us recall the RSA algorithm. Again, P and Q are big different primes. P does not equal to Q. And N is their product. Then for any number A less than N and coprime to it, we can postulate this identity, which is known as Euler's theorem. And phi of N here is Euler's phi function, which equals to the amount of numbers less than N and coprime to it, and 1 is included. So for prime numbers like P and Q, phi of P will be equal to P minus 1, since all the numbers less than P are coprime to it, and the same is with Q. It is Q minus 1. And for their product, for N, Euler's phi function equals to P minus 1 multiplied by Q minus 1, because Euler's function is a multiplicative function. Now, having all this, we can choose some random number E less than N and coprime both to N and to phi of N. And since it is coprime to phi of N, it is invertible in the ring Z modulo phi of N. And its inverse element we will call D. So it is inverse of E, so E multiplied by D equals to 1 in the ring Z phi of N, Z modulo phi of N. And also this D is the part of linear representation of the greatest common divisor of phi of N and E. And this greatest common divisor is 1, since they are coprime, relatively prime, and D and K are coefficients of this linear representation known as Bezout identity. And the linear representation here can be built by the extended Euclidean algorithm. Okay, now these numbers, E and N, we will call the public key. And the numbers D and N we will call a private key. And it is obvious that public key we share widely, and the private key we keep in secret and don't share with anyone. Time to use these keys. Okay, to encode something, we need a message to be encoded. Luckily, we can choose it on our own. So we choose some message M, and the only restriction here is that this M has to be coprime with N big, which is very likely to be true for any randomly chosen message. And we are going to encode it with the public key, which is these two numbers. So how we do it? We raise M in power E modulo N. So we compute this number, which is itself less than N, since it is modulo N here. And this is our encrypted message. And to decode this message, we need this private key we introduced on the previous slide. And we decode in the same way. We raise this number, M in power E, we raise it in power d, again, modulo n. And this equals to m e multiplied by d modulo n. And because of this identity here, since d is the inverse element of e, we will have this. So phi of n here is multiplied by some integer k, because this identity we can rewrite like this. Phi of n here multiplied by some integer. And again, all this we have modulo n. Now, this thing here equals to 1 because of the, let's recall, the Euler's theorem. And what we have left is message m modulo n, and it is exactly m since m is less than n. So we have encoded, and here's our encoded message, and we decoded it back, and here is our decoded message. And the idea is that you can't easily invert this operation of exponentiation modulo n. We will see it right now on some example, that this number here, when we raise it in some power and calculate this power modulo n, we can't easily revert it. To revert it, we need this number d. And to find this number d, we have to know the Euler's function of n big. And to know the Euler's function, we have to know the factors of n big. And as I already told you, it is hard if n big is really big. And the factors are unknown. Let's see an example. In real encryption, we have to choose really big prime numbers p and q. But for the purpose of training, we can avoid that, and we will choose p equal to 11 and q equal to 13. So now let's compute our keys. N big is 11 by 13. It is 143. And phi of n is 10 by 12 and is 120. Now I have to choose the number e, which is coprime both to n and to phi of n, and I choose it to be 17. And now we have to choose some message which is coprime to number n. And for example, let it be 7. Like, if you ask somebody how many teeth you have left, and this person wants to answer 7, but he doesn't want it to go public, and he encrypts it. And we are ready to encrypt it right now. Okay, so we have this public key, which is 17143, and we have to encode message, which is 7. So we have to raise 7 in the power 17 modulo 143. Okay, 7 in the power 17 is 7 multiplied by 49 in the power 8. all this modulo 143. Let's square 49. 49 is 50 minus 1, so it's easy to compute the square. This 2500 minus 100 plus 1, which is 2401. And we're going to compute it modulo 143, which equals to 113 modulo 143. So instead of 49 here, we can multiply 7 by 113 in the power 4 modulo 143. Now this 113, I'm lazy enough to compute its square, so I noticed that in this modulo 113 equals to minus 30 modulo 143, and minus 30 is easier to square, so it is 900. And 900 is 42 modulo 143. So this transforms to 7 multiplied by 42 squared, 143. Now 42 squared, and if you square 42 and take the modulo, you can do it yourself. You will have 7 multiplied by 49, and again everything is 143, and all this equals to 50. So 7 in the power 17 modulo 143 is 50. And this is the message. You ask somebody how many teeth, etc., and he replies 50, and you understand that you need to decode this message. Okay, we have this public key 17 143, and we have a message encrypted by this key. So write it like this, and we have this number 50. And now from this number 50, we have to extract the original message. So we have to compute the private key, and the private key D satisfies these equations. We write it down like 17 D equals to 1 plus phi of n is 120, so 120 multiplied by some integer k. So actually we have to find both these coefficients, k and d, and we are interested in d. Now we can employ the extended Euclidean algorithm, or we can notice that if we take d equal to 7, then we will have here 119, which is very close to 120. And if we take k equal to -1, we will have exactly minus 119. So we have to, instead of 7, we have to choose minus 7 to get minus 119 in the left part of this equation. So here is our private key, and in the ring Z modulo 120, minus 7 equals to 113. So to decode the message, we have to raise 50 in the power 113 modulo 143. And for those of you who are not lazy enough, I would recommend it as a good exercise to prove by your own hands that it equals to 7, our original message.